So some of you have probably done this question already. So this is integration by substitution because we've got the 4x squared plus 1 on the bottom. The derivative of 4x squared is 8x. Things match up nicely for our substitution. And we have the integral of 1 over u du, which we recognize as the natural log of c. And then this question gives us initial condition, or we're given extra information. This means we can solve for c, because we know that when x is 0, f of x is 4, so we can plug that in. Zero for x, 4 for y, and solve for c. A little bit of mental math. You have to remember that natural log of 1 is equal to 0. Again, remember when evaluating natural logs, right? Natural logs have a base of e. Logarithms solve for exponents. So one of the things that I sort of, in my head when I'm thinking about solving a natural logarithm, I'm like, okay, the base is e. I don't know the exponent, but it needs to equal 1. Well, e to the 0 is equal to 1. So then that allows you to solve for c. And now we can write the actual equation out with the value of c. So up till now, we've been doing indefinite integrals with substitution. Indefinite integrals is when there's no numbers on the top and the bottom. You're not finding an actual area. You're just finding the antiderivative. You're just working backwards. If we want to find the area under a curve and had a definite integral, what happens when we work with substitution? Now we're going to look at two different methods for doing this. All done, Theo?
Found the negative I didn't put in, so feel confident I caught my error.
So again, color coding wise, if I take out my highlighter, I notice that I have an inside function right here, 5 minus x squared. I notice my derivative of that would be a negative 2x, and even though it doesn't match up perfectly, the derivative is in there in the right form. So we've learned that it doesn't have to match up perfectly. We can do some alterations to that. So we let u equal that inside function. Then our du is negative 2x dx, but we have a positive, so we just move that negative over to the other side. And we get u to the 4 times negative du. Important to put that negative du in brackets so you don't think you're subtracting du. Some people put the negative out in front of the integral right away, or the negative out in front of the u to the 4. But either way, we're going to get, as an indefinite integral, negative u to the 5 over 5 plus c. But since this is a definite integral, we actually have to evaluate this. Normally with a definite integral, we would put this in square brackets, and we would put the numbers from 1 to 2 and solve. So there's two ways that we can go about this. First, method 1, since we solve for u, just like we did with the indefinite integral, after you've solved your integration, you would plug back in u is equal to 5 minus x squared, and we get our actual indefinite integral in terms of x. So if we were doing a definite integral of this same question, what's the notation difference with doing a definite integral? Well, we add those square brackets and we write the antiderivative down, but you don't have to write the plus c, and you write from 1 to 2. The reason we don't have to write the plus c is because in the definite integral, you subtract, right? You plug in 2, and then you subtract plugging in 1. And if you had a c in both of those and subtracted, your c would just equal 0. So now I plug in 2, I plug in 1, I get both of those answers. I simplify 204.6. This is a very typical method because it connects to what we were doing with the indefinite integral from before. You find your indefinite integral, put it in square brackets, then just evaluate your definite integral like you always did. Plug in 2, subtract, plug in 1, get our answer. But another thing that you can do with substitution is change your bounds. What does that mean? Well, if u was equal to 5x minus x squared, and you were going from 1 to 2, well, now what would you be going to? If u is equal to 5 minus x squared, and I plug in 1, then u would equal 4. And if I plug in 2, then u would equal 1. And so not only can we substitute in for u, we can also say that our indefinite integral, and if I could even write, maybe I'll write it here as a before step, 4 to 1 of negative u to the 4 du. And this is a typical place where students make notation errors. Okay? Okay? The notation error looks like this. I'll write it in, don't write this in, but I'll say, you're solving this, so you write 1 to 2, just like normal, right? Because that's what you want to solve. You do your substitution, and you substitute in u and du, but you keep the 1 and 2 there. That's actually a mistake. So in the work that I did my preliminary work, I did an indefinite integral without any bounds, just to solve it like normal. But if I kept the bounds in there, this right here is a mistake. Because as soon as I change x to u, I also have to change the bounds. And I would have to write from 4 to 1, negative u to the 4 du, to be correct notation-wise. So if you're using your bounds all the way through, you have to be careful. Then, I would plug in 1, I would plug in 4, I would subtract them. Just so happens that, well, just so happens, it should happen that we get the exact same answer. Be wonderful, eh? I'm going to teach you 3 methods, right? Methods 2 and 3 don't work, by the way. Hope you enjoyed them, but they will never work. You'll be like, what are you doing? Teaching us methods that don't work. So we have to be careful with notation. If you want to use method 1, you're going to need to figure out your indefinite integral on its own without showing the work with the bounds. If you want to write your bounds and show your work all the way, then I would suggest method 2, because once you go to method 2, you don't actually have to substitute back. And the nice thing about not substituting back is that usually you're dealing with something much easier to look at. Like u to the 5 is a lot better than having to do 5 minus x squared first and then do it to the power of 5. That's extra work. So in a lot of ways, for definite integrals, I do like method 2. Because for one, if you use method 2, you don't run into the problem of accidentally making a notation mistake that you correct later, but make it in the meantime, okay? So my preferred method would be method 2, but we'll do both. So in the setup for doing both, you would first find out what you have without just a regular indefinite integral. Don't write any of your bounds. Although if you like method 2, I would start with the bounds right away. Okay? So I will add them onto our notes as if it was showing the work correctly. So correctly, to start off with, if you had this written in, this would not be wrong. But when you go to this next equal sign, you would have to have 0 here and 3 pi over 2 there if you do the substitution. If you don't want to make that mistake, then don't write the bounds at all. Using method 1, when you substitute back, then your bounds are fine, right? 0 to pi over 2, substituted back, going from pi over 2 to 0. If you use method 2, well, now we can just integrate with the u, but have our new bounds from 0 to 3 pi over 2. And you can notice, right? Like, can you notice, I'm going to circle it in red. Can you notice that when you plug in pi over 2 into 3x, it would be the same as plugging in just 3 pi over 2 into u? You can see that the results will give you the same thing. So actually evaluating this, again, luckily both method works. No, it's not luckily. Both good methods, and you get 1/3 either way. I really see you making this mistake because it's very hard for a student, especially pre-calculus, where we've trained you to be attentive to details. It's very hard to have a definite integral and then the next step not write the bounds that were given to you in the question. You are trained to write down everything that you see. So I think almost all of you, when you start working with this, would probably still include the bounds. So I just want you to be careful that in that next step when you do the substitution, that you don't keep the bounds the same. And if you're going to change your bounds anyways, then may as well continue with method 2, because it's less work afterwards. You can just keep going with what you have. Okay, you guys can choose whichever method you like, and I'll let you do the next 2 on your own. All right, I'll put up both methods. And if you went with the bounds right away, I'll add that in. You would have had 0 to 2, and then changing it would be 0 to 4. And then here we should have 0 to 2. you solve the indefinite integral just like an indefinite integral without writing bounds, this is what you would write. If you started by either just putting an equal sign underneath this, if you put an equal sign underneath this, you are implying that those bounds are there. And if you imply that those bounds are there, in your next equal sign, you can't just take them away. They have to change from 1 to 4. Because when you change to u, your bounds change as well. That looks. Now, if you rewrite the question without bounds, then you can solve an indefinite integral, and you can go to method 1. If you do with the bounds, you can just do a much easier see how changing the bounds makes your substitution like, ooh, this is a lot easier math than plugging into here. But that's because you did the harder math earlier. It's not, I don't know if any one of them is easier or harder. You end up having to do all the same mental math calculations, no matter which method you use. It's just perception of when it was easier and when it was harder.